Yeah, I'll be starting. Good evening, everyone. Welcome to day 25 of LearnX30 by Slate Valley. I'm Amulya, your host for today's session. Those who are joining us for the first time, LearnX30 is an by Slate Valley 30 days learning journey. It is designed for the learners for practical and industrial ready skills of the technologies. And today's session is focused on quantum machine learning and optimization. So we are honored to have Mr. Gyan, a quantum machine learning research scientist at IIIT Hyderabad. He'll be sharing his valuable experience on quantum machine learning and optimization with us. Without any further delays, I like to hand over the session to you, sir.
Yes. Good evening, everyone. I too am so excited for you people to join this session because quantum machine learning is kind of weird concept, honestly to say that. It's kind of weird one, it's kind of new one. So I am very much, what can I say? First, I want to say you all thanks for coming to this session. Why? Because this is a very weird topic and all. It's okay. Just try to understand the basic concepts. I won't go that deep into mathematics and stuff because, as I said, quantum is like a physics thing and there will be a lot of mathematics and stuff. But in this time, I don't want to bore you guys with those mathematics and all. I'll just tell you the concepts of whatever I have learned for the first time when I was like, yeah. So there's this lobby, guys. Okay. So first time I just do it and I'll just let you know why quantum ML is the future of machine learning. So you can directly start with that thing. So I will just share my entire screen. I have a small presentation which I made actually. Sorry. Yes. So I think you guys are looking at my screen, right?
Yes,
Is
it's
my
visible.
screen visible? Yeah, cool.
Yes.
So, okay, this presentation, this PPT is just for normal interactivity sake, but most of the things will be there directly by the audio thing only. So I will be mostly speaking stuff rather than just looking at the presentation. So please concentrate most on my speaking stuff rather than directly on the presentation. So if you have any doubts or something, either we'll be having a QA session at the like last 10 minutes or something, or else you can also like raise your hand and you can also ask your queries in the meantime. So it's not a problem. Yes. So first thing, quantum machine learning. So before going to quantum machine learning, it is necessary to know about what is quantum computing in the first place. So normally we know classical computing. So classical computing deals with the everyday stuff which you see. You have CPUs, you have GPUs, and you are thinking like, okay, so we'll work on them and they will just show as very high processing powers and something like that. And recently we've seen like a lot of advanced technologies also. So if you follow NVIDIA and all, so there are lot different variants of GPU cards and everything being published by them. So they all are very much advanced. And we think like, okay, so this is the end of AI or this is the advanced version of AI or something like that. But let me tell this thing to you. So all these stuff, all these classical stuff has only a certain amount of radius for their working. Why? Because after that certain radius breaks off, then your classical system can't work. Okay. So for those kind of situations, so how to handle those kind of situations? For example, I will tell you this. I think most of you guys who know classical machine learning and stuff, like you having like NP problems, N problems, P problems, and all, right? So let's go with the classical NP problems. So if you go with a traveling salesman problem, let us go with the traveling salesman problem. So what does it mean? I think most of the people know about it. So there are a particular number of nodes, which are like the cities, and out of those cities, what we are going to do one time. So there should be a travel like salesman or a delivery guy. You can say it as a delivery guy also. So all these nodes, that particular person should cover all these nodes in a single iteration and should be reaching his initial point with a very low cost. That is with low cost and like high efficiency. So that means at a very short amount of time and with very short amount of cost, he should attend all of these nodes, that is all of these places, and return back to its his starting point. Okay, so this is like problem. This is like a common. This is like combinatorial optimization problem. So which is a TSP problem. So if we are using classical machine learning techniques, so in order to solve this, we have a lot of classical machine learning techniques. Most widely used is simulated annealing. So we have like simulated annealing technique, and if you want to look at the DSA of it, so you have a lot of techniques to solve this particular thing. But let me tell this thing to you. So initially, if you're having like four nodes, that is a particular guy, he need to deliver a delivery at the four places in a city. So let us take Hyderabad. In Hyderabad, there are four places, like four like areas, like Secunderabad or Jubilee Hills, Banjara Hills, and two are High Tech City and Madhapur. Then if we use a classical optimization technique, like as I mentioned, simulated annealing, so it will work nicely. It will obviously work nicely and it will give you him the solution. Like, okay, so first go to point A, then point C, then point B, then point D, and then come back to point A. So it will give an area for him. It will give him a linear layout so that he can like pass through all these points and with a low cost. Okay. But now let's do with this thing. So four nodes is okay, simple. What if it is 50 nodes? So if it is 50 nodes, again your efficient answer will be coming up, but with some time. Like for example, if you are solving for four nodes, it will take like 0.2 seconds or 20 milliseconds or something like that in order to give you an answer. But if you expand it to 15 nodes, what will happen? It will be giving at okay 2 seconds or 1.5 seconds or something like that. Expand it to 500 nodes. Then what will happen? It will be giving you the solution in 20 seconds or 40 seconds or something like that. If it is 5,000 nodes, then it will be so much high. Like it will become like 500 seconds or something like that. So as you can see here, the problem with classical machine learning is when your number of values increases, like number of terms or number of constraints or number of values increases. That is, if you want to say it mathematically, if the number of dependent variables increase for your decision, then what will happen? The complexity of your problem increases. And as the complexity of your problem increases, your classical machine learning techniques won't be able to handle that. Okay. So that's the reason most of the people who are thinking like AI will be completed after some period of time, because right now we're in agentic AI. So afterwards we'll be having like industrial AI, like moving stuff and all. Afterwards the AI will be integrated into completely IoT devices and IoT stuffs, and we will be having an automobile kind of AI where we can see the things moving with AI and all. When people claim that that is the end of AI, but that won't be the end of AI, because as the things increases, the problem statements increases and everything increases, but your AI won't be able to handle them. So, in order to handle even complex tasks with like 5,000 nodes or 50,000 nodes, also, it should be able to give the answer in like 2 milliseconds. For that, you are having quantum computing. So, normally, if you want to know about quantum computing is nothing but a classical computing in a very advanced manner. Okay, so first of all, what is meant by quantum? So it's like it all started when Richard Feynman taught to, what can I say, simulate some behaviors of atoms in a computer. And then he came to know that, as you say, Richard Feynman is like a famous quantum physics guy, and he's a very great scientist. So he wanted to simulate some stuff, simulate the behavior of quantum actions in a classical computer, and he got to know that he is not able to simulate it. That is, the quantum movements are so fast and so vast and highly complex that the classical computers, that is the CPUs they are having, are not able to process it. So what he taught is why can't we make a computer having quantum properties? Okay. So first of all, what do you mean by quantum properties? And the quantum real meaning is very small. So if you know physics so nice, like if you're so enthusiastic in physics, you'll be knowing the difference between classical physics and quantum physics. So that's the problem we are having right now in this universe. So the thing is, classical physics, mein, it is Newtonian physics. Okay. So Newton's third law of motion or everything. So everything comes under classical physics and classical mechanics. But if you go deeper into the scale of atoms, that is 10 to the power of minus 9 and 10 to the power of minus 15 meters, then you will be seeing that the atoms or the particles are not following your classical rules. So they will follow a completely new set of rules called quantum rules. Okay, quantum physics. So that's where your quantum physics came out. And this quantum computing uses this quantum mechanics principles, and then it will solve your problem. So this is quantum computing. Okay, so first quantum physics came, and class we as quantum physics is way more advanced than classical physics. So what we try to do until we try to integrate these quantum physics principles into your computer, and that makes you make like that brings you a quantum computer. Okay, now. So what are those principles? I think I'm having that. Yeah. So these are the core. So yeah, here we'll be having the core principles and stuff like that. Mm, okay. So in this page, we'll be just discussing everything. So firstly, what is core principles? So as I already mentioned, classical physics equal to classical computer, quantum physics equal to quantum computer. So what is the difference? Okay, so if you like normally in physics, man, what we'll be saying, so if you go to your 11th class or 12th class physics and chemistry also, you'll be having these things. Like you'll be having atoms and you'll be having this quantum numbers around the atoms and all. You'll be having a string wave-like structures and electronic waves, all these things will be there, right? So that is quantum physics, honestly to say. So if you will be observing quantum physics more in chemistry than physics subject in your 12th grade and all. So if you see like Bohr's atomic radius or something like that, so this all are comes under quantum physics only. Now, so what is quantum physics? Is this the physics which is like it? They are the rules followed by the particles which are in a quantum level. Quantum level in the sense 10 to the power of minus 15 meters. Okay, from 10 to the power of minus 15 meters, you'll be having a quantum level. So there the particles behave completely weird compared to your classical level. So if you see two cars moving, like if you go to a road and if you see two cars moving, so they follow classical mechanics. Why? Because they are in the scale of classical physics. But similarly, if you go to 10 to the power of minus 15 meters, if you zoom in and go to 10 to the power of minus 15 meters, the things which they follow will not be equal to the physics which your car follows on the road. Okay, so that thing which those small particles follow is quantum physics and quantum mechanics. Now, let's coming to our computing theorem, like in terms of computing and all. Firstly, classical computers deals with bits. Okay, so if you see anything, if you see like any information transfer, anything. Okay, so first of all, your computers or your devices, everything comes regarding communication. First main thing is communication and interaction, right? First thing is communication only. So even your electrical signals which is powering up your computer also deals with those communication stuff only. Okay, so the things from CPU, the CPU processing your like informations and everything, like all comes under communication stuff. So the basic unit which is required for your computer or phone or anything to process is bits. Okay, so there are bits which are like information carriers. So that's why it's a communication. It's not like signals communication or something. So if your CPU is working something and if your CPU is processing something and giving you the answer, it is because it is processing with the help of bits. So bits are information carriers. So whatever you give, they all will be transferred in form of bits only. Okay. So classical bits, what it will happen in classical, okay, so shall go like this. Classical bits, they have only binary options. If you like normally if you say like classical bits, they have binary option. That is either they are one or zero. That's it. Okay. So initially you can have either one or zero. It cannot be more than one or less than one. It cannot be between zero and one also. It is either one or zero. So that's how your classical bits work. Okay, and these bits make up 1 byte and 1 byte make up megabytes and all, so that relates to your communication and all your processing. So that's why I'm telling like basic unit. So basic unit is bits which your classical computer works on is bits. So if you take a bit, it has only 0 and 1. Okay, like it's like a binary value. Okay, it's like a binary value having only 0 and 1. Now, what will happen until? So if you're having 0 and 1, let us go like this. So let us consider you are having like 5 bits. Okay. So you're having like 5 bits and you want a particular solution. Okay. Let us consider the particular solution is 10010. Okay. So for those 5 bits, as they have only 0 and 1 option, the particular solution can be 100 and 10. Let us consider like that. So now, if your classical computer want to find that answer for those 5 bits, how much iterations it will take? So this is a problem of your probability and statistics, like permutations and combinations. So if you're having five guys and each having 0 and 1, so it will be 2 to the power of 5. So totally there are 2 to the power of 5 options. So out of all these 2 to the power of 5 options, it should choose one option. That will be your correct answer. That is, as I mentioned, 10010. So what your classical computing will do, Ante, as it is a binary guy, either 0 or 1. So what it will do? First, it will check the first option and it will be 00000, 5 zeros. Afterwards, it will go back and it will check the second option, which is 40 followed by 1. Afterwards, it will go back and check the third option, which is like 3010, like that. So like that, it will check until it gets your desired state, which is 100 and 10. So look at this time processing. For example, if your final answer is 5 ones, then it should perform all the 2 to the power of 5 iterations and the 2 to the power of 5th iteration will be your final answer. So it should perform all of these iterations. That's it. That means it should check all of these paths. It should check all these paths in a sequential manner. Why? Because your classical bits has only one possibility, either 0 or 1. So that means your bit can carry only one answer. One bit. Your one bit can carry only one answer. So that's why it should check everything in a sequential manner until it gets a desired state. So you can only guess. So as I mentioned, if it is 5 bits, it will take 2 to the power of 5 iterations. If the final answer is like if the answer is a final option. Let us go that for like 5,000 bits or like 50,000 bits or like 500,000 bits, then how much iterations it should take your class CPU or your classical computer? It should take 2 to the power of 500,000, 2 to the power of like 5 million iterations if your answer is a final answer. And that's the thing which is making your complexity increase and which is making your time increase. As I mentioned in the beginning, in TSP problem, if you increase the number of nodes, I said the time will increase, right? So this is the reason the time will increase. Why? Because it will check all the paths in a sequential manner. Why that to why in a sequential manner? Why? Because one bit can carry only one answer. If one bit carries only one answer, it is able to check in a sequential manner rather than all at the same time. Why? Because one bit cannot carry more than one answer, right? So it can't check process like that. So for that's the reason it is going in a single manner. It is like, okay, first I will be like this, and then I will be like that, and then I will be like that. Like that is one. So that's why it's a sequential manner, and that makes your time more. Like it increases your complexity and reduces your efficiency. Now, let's come to classical computing. So, this is the entire reason why quantum is very fast. I mentioned like quantum is very fast in the beginning. So, why means because of this point, principle. So, there is this principle called superposition in quantum mechanics and quantum computing. In quantum mechanics, there's this principle called superposition. So, there are like three main guys, which is like superposition, entanglement, and measurement. Okay. Only because of these three principles, your quantum computing is way more superior than your classical computing. First, let's go with superposition. So, what is superposition? Ante? Simple. Classical computers has bits, right? Your quantum computers have something known as qubits. Okay. So, it's like QU bits. They have something known as qubits. So, what are these qubits? Ante? Classical computers bits have either 0 or 1. Quantum computing qubits, they can have anything between 0 and 1. Okay. So they can be 0 and they can be 1 also. Understood? So yeah, that's how your qubits work. So it's not limited to only one option. So at that particular point of time, your qubit can be either 0 or 1, both of them simultaneously. Or it can be any state between these 2 points. Understood? And that is making your quantum computers faster compared to your classical computers. Why? Because let us go to that sequential manner now. So in classical, what did I say? One, like sequentially, it will check 2 to the power of n options. But when you come to quantum, what will happen as each qubit can handle more than one options within it. Okay, it is not limited to only one option. It can handle more than one option, either 0 or 1. So not either, both. It can be like 0 or 1 or both 0 and 1. Your qubit can be 0 and 1 also. So if you are having a qubit which can have more than one option, is it necessary for you to go in a sequential manner, or is it you can like complete everything in a single go? You can complete everything in a single go. Why? Because your qubit has more than one option in it, right? So you can take that entire qubit. So you can take 5 qubits, which can act like more than one option. And then what you'll do, you'll just find the probabilities of them. So that comes to your third point, which is measurement. So what you'll be doing in quantum computing, Ante, instead of going everything in a sequential manner, you will take those 5 qubits, and then what you'll do, you will directly measure them. That means in that measurement process, what will happen? That these all qubits are there, na, which are in more than one state. So that 0 and 1, that is known as a state. Okay, so your classical bit is in a state 0. Your classical bit is in a state 1. So that is known as state. That 0 and 1 is known as state. So if you want to measure something in quantum, what you will do, you will take that 5 qubits and then you will perform a measurement on it. So measurement is like some external thing which you apply on a set of qubits. I will come to it later. So what will happen when you measure untype? So these qubits, which are in a random state of both 0 and 1, they all will be fallen back to a state with higher probability. Okay. So instead of checking everything in a sequential manner, what will happen in this case? You are taking one thing, you are taking your 5 qubits, you are directly measuring them. So then what will happen until all of these qubits which are having states in it will eventually decompose to any one of the state between 0 and 1. Okay. And that too, how they will decompose? They will decompose to a state where it is in heavy probability. So let us take those 5 qubits. The answer is 10010, right? So instead of checking everything in a sequential manner, we will directly measure it. Then your first qubit will go to a state 1. Why? Because that is high probability. So you are having high probability for state 1. And second qubit will be going to state 0. Third qubit will be falling to state 1 again. So it's something like that, Anwar. Okay. So they all will be falling to a particular state where it is highly probable. Okay. Like for the state, if it one state is heavy, has heavy probability, it will fall to that one state. So that make your quantum computing faster. So the main thing is the superposition concept. That is, unlike your classical, where one bit has either 0 and 1, in quantum, what will happen? One qubit can be more than 0 or 1. So it can be both 0 and 1 also. So what will happen? You are having more than one way to check the answer. You don't need to go sequentially. Parallel in a single go, you can check them. Right? Why? Because it's having more than one options. So that makes your quantum computing faster. So if you want to go in a mathematical manner, if you see classical, it is 1 in 2 to the power of n. So it is 2 to the power of n iterations. But in class quantum computer, what is happening? 2 to the power of n in a single go. So in a single go, you're checking all the 2 to the power of n guys. So that is in classical, when you're checking one guy, in the same time, you're checking all the 2 to the power of n guys in quantum. So that makes your quantum faster than your classical only. Okay. So that's the deal. So that's your first concept, superposition. Now coming to real life example, how you can define superposition. Okay. As I mentioned, car, right? So let us consider a car which is going in a straight road. Then in classically, what will happen? It will just go there. That's it. There won't be any change. But in quantum, what will happen? Ante? So it will be going right. So you can see a single car going, and you can see the same car going on the other side of the road also. That is same car, same person, same thing. The same entity can exist in more than two places at this, I mean more than one place at the same time. So that is superposition. That means I can exist here and I can exist somewhere also. Same physical quantity, same physical entity, not a doppelganger or something. Same physical entity can be here and can be somewhere also at the same point of time. That is superposition. Okay. So you are having multiple guys of the same property. Understood? So that's why your quantum is faster. Now, coming to second principle, which is entanglement. So what is entanglement, Ante? So entanglement deals with your measurement fast, like faster measurement and stuff like that. So entanglement concept, we can go it like a heavier connection between two guys. Okay. So that is if you're having a qubit 1 and if you're having qubit 2, then these two qubits are said to be entangled. So when they entangled, when they are heavily brought close to each other in extremely cool temperature. So you are having this principle, right? Which is like charges repel and unlike charges attract each other. That principle will be there, right? Coulomb's force of attraction. What will happen ante, if you are in a very cool temperature, that is minus 300 degrees Celsius or minus 500 degrees Celsius, something like that, then what will happen? This Coulomb force of attraction will reverse, Anamata. That is, they will become like charges attract each other and unlike charges repel each other. It will change like that in a very cool temperatures. So we will be using that concept to entangle two qubits. So let us consider two qubits. And if you entangle these two qubits, what will happen in a sense? Okay, let us bring them close at a very cool temperature. Now they are said to be entangled. So after they are entangled, if I separate them, and if I keep one guy here in our solar system, and if I keep other guy in an Andromeda galaxy, which is like 200,000 light years away from us, approximately, Andromeda, man, we kept another qubit. Now, what will happen, Ante? So, as I mentioned, when we measure a qubit, it will decompose to one state. Okay, so normally your qubit can be in many states, as I mentioned. But when you perform measurement, it will decompose to one state, that is either zero or one. It will decompose, right? So if you have two qubits which are entangled, and if you push one qubit to your Andromeda galaxy, one you're having in Milky Way galaxy itself. Now what will happen at that? If you measure this particular qubit in Milky Way galaxy, I measure this particular qubit here, and if that turned out to be one, so if this measurement turned out to be one, then automatically without measuring or without considering or without even looking, that second qubit out there in the Andromeda galaxy has a measurement of zero. Okay, this concept is known as entanglement. Okay, so what will happen? Two qubits, entangle them. Okay, two is a minimum number. You can entangle any number of qubits. Two qubits, entangle them and keep one qubit here and keep one qubit somewhere else, many light years away also. So if you measure this qubit, which is in Milky Way, and if that turned out to be one, the second entangled qubit, even though whether it is so far, and even though if you measure it or don't need to measure it, even though if you see it or no, that qubit's answer will be zero. So it will be opposite anamata. And that concept is known as entanglement. And why this is necessary, and by this itself you can understand why, because faster communications. So now there's a problem in this thing. Not a problem. There's like a physical like physics may it's a wrong. Why? Because according to physics, what's the rule? The rule is nothing travels than the speed of light. Right? That's the rule. If you see physics. But in this case, what is happening? Your second qubit is in Andromeda galaxy, which is like 200,000 light years away from us, approximately. Then what will happen if I measure the qubit here in Milky Way? If it turned out to be zero, then that information should pass in a speed of light to that qubit. Okay. So the information like, okay, so bro, I am one, so you need to become zero. So that is also an information, right? So that information should be passed in the speed of light to your second qubit in your Andromeda galaxy. See, even if it is passing in the speed of light, it will take how much time? It will take more than 200,000 light years. Okay. So it will take more than 200,000 light years for that information to travel because everything travels at the speed of light. Nothing travels at the speed of light. So let us consider close to speed of light and it will take that much time. But in this case, what is happening? The moment you come to know it is one, that will become zero. So how the information is traveling or from where the information traveling is a mystery. So if we solve that, then you'll get a Nobel Prize because there's this paper called EPR paper. So in that EPR or ERP paper, so in that paper, Einstein wrote this theory. Like Einstein, like raised this thing. Like you say in entanglement, this will happen, right? But nothing travels than the speed of light. So from where this information is going to that qubit, so like that, Anuma. So yeah, so we call it as EPR paradox or ERP paradox. I think it's ERP. So we'll call it as ERP paradox. So nothing travels at the speed of light, but this information is going to that guy, the other qubit, in an instant. How? So if you solve that, you'll get a Nobel Prize. So that's your entanglement. So what you can see with this, it is a heavy, like it will provide you faster communications. And if you see the teleportation stuff, like normally people studying about quantum and all, they all saw some news coming up like Google Labs made they teleported information, they teleported this thing. So that thing is there, right? So the teleportation is not like your classical sci-fi movies where this phone will vanish here and it will pop up somewhere else. It's not like that. So that teleportation is the information transfer. Okay. So what I did that time, I'll take two qubits, which look like this. And then what I did, I entangled those two qubits, which look like this, like two phones, let us consider. And then what I did, I vanished one qubit. Okay. So I decreased the one qubit. I extremely cooled down one qubit. And I kept it somewhere else. I kept it somewhere else. Okay, it's not like I didn't keep it somewhere else. I kept it somewhere else. That is, if I'm in Australia, I kept it in US or something like that. And then what did I do? I entangled these two guys and I kept one guy there. And what I did, I measured this qubit here. Okay, I measured this qubit in Australia. And the moment I measure this qubit here, what will happen? I'll be knowing the measurement of that qubit, right? So what is happening the moment I measure this qubit in Australia, it will be destroyed. Okay. So the moment I measure it, I destroyed it. Now here I'm not having any qubit. Then there I will create a qubit automatically. Then that qubit's measurement will be the opposite of this one. So the moment it got vanished here, it like what can I say? It popped up there. That is what is popping up. This same entity doesn't pop up. The information of this entity popped up. So initially there are two qubits only. Two qubits very far from each other. What did I did? One, I hid it somewhere, and this guy I measured. And as soon as I measured this guy, I destroyed this guy. And as soon as I destroyed this guy, I created this guy. That is, I didn't create, I brought him up from hiding. So this guy will be the opposite information. So what is happening in here? So if you look in an outer perspective, what is happening? This thing is there, this vanished, and this came up, right? So people call it teleportation. That's not teleportation. That's just the measurement of two entangled qubits. That's it. So this is entanglement. And measurement, as I said, that's a third principle of quantum. So measurement means it's a completely different concept. So what will happen is you will externally factor it. Yeah, so you will externally give something or you will externally push something to that particular qubit, and then it will fall down to a particular state of high energy. High energy state is your, what can I say? Answer always. So yeah, it can be either high or it can be low. So that's an energy landscape. So that depends on your optimization. So mostly low energy we will take. Yes, mostly low energy we will take. That low energy state will be your final answer. So what will happen until there will be this qubit. So externally you will affect this qubit by giving heavy electrical signals or by giving heavy heat or by that's it. Only two ways are there. Heavy electric so light electrical signals, light, and heat. So there are three factors in which you can measure. So either you can give heavy electrical signals, or you can give heavy heat, or you can give heavy light. So if you give three of them random, not like random, like suddenly, then what will happen? This entire superposition state will decompose to a single state of high probability. High probability means low energy. So it will all decompose to a low energy state. And that low energy state is your final answer. Okay. So that is your measurement. So through these principles, your quantum computing is like way more, like it provides more advantage than your classical computing. Now qubit representation. Okay. So as I mentioned, so it's like this. So as I mentioned already that your qubits are different. So they look something like this. So this is how a qubit looks like actually. Okay. So normally if you take bits, as I mentioned, your bits are like a classical spheres only. It is 0 or 1, up and down. But your qubit has something like it is a sphere. Okay, qubit is a sphere where you are having two states in a z-axis. Okay, 0 and 1. This up or down is not mandatory. Sometimes you can keep up as first state and down as zero state also. That's your wish. Now, a qubit's particular state is determined by uh, so I should I think write that. Okay, so I will okay, that's determined by a superposition formula. Okay. So it's completely dependent on probabilities. This one's yeah. So if you look at this thing, so this is a superposition state of a qubit. So how are you gonna go on that? So you are going to represent a qubit in the form of a combination between 0 and 1. So instead of this 1 by root 2, you can keep alpha, and instead of this 1 by root 2, you can keep beta. Okay, let me consider. Okay, this guy, yeah, this guy. So this is your representation of your, what can I say, qubit. Okay, this is like state vector. We will call it as state vector. This phi is done that we will call it as state vector. Okay, so how this happens, Ante? If you take the qubit here, so normally classical bit A equal to 0, classical bit B equal to 1. That's it. But qubit, as I mentioned, is the combination of these two guys. Like you can have both of them, right? So what will happen? This arrow mark is there, na? This arrow mark represents your qubit state. Okay. And this arrow mark is like it can be anywhere inside this sphere. So this is a sphere and it can be anywhere inside this. That is, you're having a ball and it can move like this. Okay. Throughout that sphere, it can move in any direction, like up and down or something like that. Okay. And through that, you're going to define a state vector. So the basic definition of state vector is this one, where alpha is the probability of the qubit being in the state 0. Okay, this is the probability of the qubit being in the state 0, and beta is the probability of the qubit being in the state 1. Okay, so this is how you represent a qubit. So if you take a qubit in superposition state, that will come like this. Yeah, that will come something like this. 0 plus 1 by root 2. So superposition state means exact. So this will be coming when you apply Hadamard case. So yeah, I will tell that to you later. So that is like exact. So it's like a middle point. So it is both 0 and 1 simultaneous, like 50% of probability. So 50% for 0 and 50% of 1. For that, you'll be having this guy. Why? Because the answer will be 1 by root 2 of state 0 plus 1 by root 2 of state 1. So this is how you are representing a qubit. Okay, you will represent a qubit by using state vector, using the probabilities and all. Understood? So that's it. And yeah, so this is how you represent a qubit. Now, how are you going to perform? So what's the thing? Qubit represent quantum gates. Yes. So what do you mean by quantum gates? So you are having, okay. So if you want to apply quantum mechanical formulas or quantum computing things and all, you can't just go them like casually. So you will be using a separate gates called quantum gates. So they are like the explicit gates which can alter your qubit state vector. Okay. So let me go like this. Yeah. So I'll just tell simply. So if I will go like quantum gates, yeah. So these are the quantum gates. So okay, okay. First I'll tell casually. So I think you know about very well about your classical gates, right? So if you there's this subject called COA, which is like computer organization and architecture. So if you look at that particular subject, then what will happen? You'll be knowing more about the gates in your classical computers. So classical computers have which type of gates? AND gate, OR gate, NOT gate, XOR gate. So you have these all gates, right? So why are you using these gates? Like what are these gates? So these gates transfer your bit state. Okay, that is 0 bit and 1 bit. So if you want to perform something using those two bits, you will apply a particular gate. So if you want to perform an like true or false thing, like AND operation, so you're going to use an AND gate for those two bits. That is this guy. Okay. That if you want to perform an OR operation, you will be using XOR gate. Or for exclusive OR, you will be using XOR gate. So why we need these gates? These gates are used to transfer the state of your bits. Right? In your classical computer also, you're having gates, like small things it will be there. Like if you look at this inside structure of your hardware, you'll be seeing small things. So that are the gates. So which are used to transfer the state. Similarly, if you go to quantum computing, so for qubits also need to change their state. Initial state itself is not the final state, right? As I mentioned, measurement, what will happen? They all decompose to one state. So that is also not like if you take a normal qubit, I will measure it, the answer will come. It's not like that, right? You need to process something for these qubits such that they all fall to your high probability state. Okay, just like that, they won't fall, right? So you need to do some stuff so that they fall into your high probability state. Okay. So for that, you need to alter these gates also, alter these states also. So as I mentioned, the qubit state vector, you need to alter this qubit state vector also, such that they all can fall into a high probability state when they are measured. So in order to change their states, you'll be using qubit quantum gates. So there are no lot of quantum gates, but the most widely used gates are like Hadamard gate, Hadamard gate is most widely used quantum gate, and we'll be using C naught gate. C naught gate is mostly used to perform entanglement between qubits. So if you have qubit A and if you have qubit B, and if you want to entangle these two qubits, you can use C naught gate directly. So if you use C naught gate directly, then they will be entangled. Okay. And Pauli's gates. So you're having some gates known as Pauli's gates. Poly X, Poly Y, and Poly Z. So these are some gates known as Pauli's gates. So that's defined by Pauli, like Paul. Yeah, Pauli, I guess. So Paul Dirac. I think you know Paul Dirac, right? So yeah, Paul Dirac is the scientist who created these gates and all. So yeah. So these are some of the main gates you're going to use. And if you're having two qubits, and if you want to make these two qubits like, if you want to bring those two qubits in a superposition state, you're going to use Hadamard gate. Okay. If you're having a single qubit, if you want to make that qubit a superposition state, you should use Hadamard gate. That's why I tell Hadamard gate is the most widely used gate. Why? Because it can convert a quantum qubit state to a superposition state. And so superposition state means what? As I mentioned before, state vector 0 plus state vector 1 by root 2. So that is known as a superposition state, clean superposition. Okay, if you want to convert a normal qubit state to a superposition state, you're going to use Hadamard gate. Okay, so this is known as the Hadamard gate. So classical math, you will be having a normal thing. So you'll be having a truth table. And using the truth table, you will be finding the answer, right, in classical. In quantum, so even classically also you have matrix, but in quantum, the matrix is most important. Quantum, you don't have something known as truth tables and stuff like that. Okay. Quantum gates, what will be having? You will be having matrices. So what you will do? So this thing is there, right? So this is alpha. So this is alpha, beta, and alpha, beta respectively. It will be like that, Anumat. So if you're having two gates, it will be alpha, beta, and alpha, beta. So the rows and the columns both will be alpha and beta. And then what you'll be doing, you should multiply your state vector with these gates, Anumat. Okay. And then there will be an answer, and that answer will be your transferred state vector. So this comes under mathematics. So yeah, for simple explanation, I'll go with this. So yeah, this is the reason. So this is an X gate transfer. So X gate transform, let us go like this. So what is an X gate will do? X gate will change the position. So if the qubit is in 0 state, it will change it to 1 state. If the qubit is in 1 state, it will change to 0 state. That is your X gate transfer. So that's why you will use X gate. So this is the matrix of your X gate. So if you look back now, this is the matrix of X gate 0, 1, 1, 0. Okay. And this vector is there. Right? This column vector represents your 0th state. Because first thing is 0, second thing is 1. Always. 0, 1. Okay. So this represents your 0th vector. So 0th vector is this one. So if you, this is known as ket notation. So there is something known as bracket notation through which you are representing the states of your quantum things. So if you look at this, there is a ket notation. So this is 0th vector in a ket notation. So 0th vector can be represented like this. Why? Because first guy is your 0, second guy is your 1. Okay. So this is your, what can I say? 0th vector. That is this represents a state in, this represents the qubit in 0th state. Now, as I mentioned, X gate, what it will do, it will transfer. So if you're having 0 vector, like 0 qubit state, it will transfer into 1 qubit. So simply just multiply. Simply just multiply. Like, okay, not multiplication, you'll be using something known as cross product. So after applying cross product, you'll be getting this answer. So that is what will happen until your state will be transferred. And this is your 0 and 1, first vector state. Okay. Similarly, this guy also. Understood? So this is how your gates are used to change the state unlocker. Yeah, as I mentioned, you will be using this guy. Okay, this notation you will be using. So this all comes under mathematics. So let's skip this part. So this is how your state vector can change by applying gates. Similarly, if you apply a Hadamard gate, so Hadamard gate is what, 1 by root 2 of 1, 1, 1 minus 1. If you just multiply that Hadamard gate with this guy, that is your 0th vector, you'll be having an answer of 0, by root 2 plus 1 by root. You'll be having two different guys. So it works like that. So let's say at the mathematical part. And yeah, so this is it. Now quantum circuits. So quantum circuits are so simple. So as you know, quantum circuits are nothing but the continuous arrangement of quantum gates. That's it. Look at this. This is a quantum gate. So quantum circuit. So this is like a big quantum circuit. Now, this is a C naught gate. So I applied a C naught gate, and then next iteration I applied X gate, Hadamard gate, and all gates, poly Y gates, and this thing represents your measurement. So you are measuring an amount. Okay. So this is known as quantum circuit. A quantum circuit is nothing but as something which has a lot of gates in it. Similarly, what is a circuit? A circuit is something which has a gates in it, right? So that's it. So that's your quantum circuits. And these are all normal things you are saying. So they are workflow. And first, yeah. So how to create a quantum circuit? Simple. Firstly, what you're going to create, Ante, you will be creating a qubit. So these straight lines are there, right? So these straight like Q0, Q1, Q2, Q3 and all. So these all are qubits anamata. So in this is an operation which has four qubits. Okay. This gate is Hadamard gate. So initially what you're doing, I'm trying to make every state as superposition state. So I brought all states to superposition state, and then I applied Z state here, and then I applied C naught gate here. That means I entangled this Z state to all the three qubits I'm having now. And then I apply Hadamard gate again. So yeah. So this is a quantum circuit which has a lot of gates in it. So initially you need to create the qubits. After creating the qubits, you need to bring all the quantum states into superposition. For that, you need to use Hadamard gate. And afterwards, if you want to entangle qubits, you can use this thing. It will be an entangled qubit state. Okay. So yeah. Now quantum machine learning. Okay, I will explain quantum machine learning simply because time's not that much. Okay. So yeah, that's it. Okay. So it's a quantum class, right? So it will be way more hard to explain everything. So let's go with quantum machine learning. Simply to say, what is quantum machine learning, Ante? Machine learning principles you are applying in a quantum computer. So that is quantum machine learning. So if you take classical machine learning, so every machine learning algorithm is what? It is a mathematical concept. Okay. So every machine learning algorithm is a mathematical concept and that works by bits and something like that internally computer man. So quantum machine learning is a field of machine learning which you can apply in a quantum computer. Okay, they all have completely new guys and new concepts. Okay, so you'll be using quantum machine learning concepts in that. So quantum machine learning concepts in the sense like new algorithms which uses quantum principles. So as I mentioned, your classical machine learning uses what? Classical mechanics and classical physics and classical principles, right? Similarly, your quantum machine learning uses quantum principles, Anamata. Okay, so they are like a completely new guys, like completely new set of new area where you can apply machine learning in a quantum level. So for that, you're going to use quantum principles. So that's the same thing. Simple. It's nothing much different, or it's not a new concept or something. So what it is, Ante, algorithms built by using quantum principles. That's it. So classical machine learning, you are having simulated annealing algorithm, and you are having. So if you look at normal machine learning, so you're having regression algorithms, classification algorithms, and all this stuff, right? So these all are algorithms which follows your mathematics, which are like classical mathematics, right? So this all follows your classical mathematical stuff. Okay, classical mathematics means classical physics. But these quantum machine learning algorithms follow quantum principles, Anwar. So they all follow quantum mechanics, quantum physics, quantum principles, and all. Okay. So yes. So the main guy is not. This is not it. Okay. So if you look at quantum machine learning, the main guy is quantum support vector machines and quantum neural networks. So as I mentioned, a quantum circuit is there. Na? So this all depends on the circuit only. Okay, you're going to build a circuit which is like a very guy who is having a lot of gates in it, and those gates arrangement will define which algorithm you are using. Okay, so if you are arranging those gates in a particular manner, and that determines that algorithm. Okay, so if you go into gates, they are like VQC. We are having something known as VQC, which is known as variational quantum circuits. So these variational quantum circuits are the like quantum circuits, which are having gates. And each gates have a parameter called theta in them. Okay. And based on that parameter value, your final answer will be defined on what. So this parameter is analogous to your, if you go to classical machine learning, let's go to your linear regression. So in linear regression, what you need to optimize your beta values. So if you find the best beta values, then your final answer will be the best answer, right? So make these theta values of your quantum gates analogous to this beta values in your linear regression. Okay. So what you're going to do on these theta values are there, which are in the gates. So these theta values mostly will be there in rotational gates, rotation gates of quantum. So we are having something known as rotation gates. Yes, poly X, poly Y, and poly C. These are the rotation gates. So rotation of pi gate or rotation of pi in like Y axis and rotation of pi radius around Z axis. So this thing is there, na? So this pi is there, right? This pi is not by default. This pi is value. So this initial pi is 3.16, right? So you can make it any value. You can make it like 2.75, you can make it 1.23 or something like that. So this is your parameter for your gate, for your circuit. Okay. So you want to perform that, like you want to tune your circuit in such a way that these parameters are there, right? So the radius through which it should rotate, or the time through which it should show the answer, or the number of gates it is applying. So those are the parameters will be there. So you need to optimize these parameters in a perfect manner such that you'll get a good answer. So that is your mission, quantum machine learning. That's it, nothing else. So if you go to linear regression and everything, what is a simple concept? Simple concept is optimize the parameters. Okay, optimize the parameters, you'll get the good answer. Similarly, quantum machine learning, what will happen? You'll be having circuit, quantum circuit, as I mentioned. You'll be having different gates, and those all gates have parameters. Not like all gates. Hadamard gate doesn't have, C0 gate doesn't have parameters, Hadamard doesn't have parameters. All these poly gates have parameters. So these are known as rotation gates. So these rotation gates have parameters. Okay. So you need to rotate the state in a particular angle. So that particular angle will determine your efficiency, and that particular angle will determine your answer on quantum. Understood? So you need to apply. So in VQCs, what will happen? Automatically, it will update the parameter by itself. Okay, and then it will automatically give an optimum parameter. So this is how your machine learning happens in quantum machine learning. And the main guys are quantum kernels and feature maps. Feature maps are simple. So classical information, you need to update it into a quantum information. Okay, so classical information you cannot give to quantum. Why? Because classical it is bits, right? Quantum it is qubits. So the changing of classical, the mapping between classical to quantum is known as feature maps, Hanuman. Okay, so these feature maps determine the mapping of classical state to quantum state. That's it. Okay, for that we are having many maps like ZZ feature map, poly feature map we are having, and Z feature map we are having. So these all are different feature maps we are having. Okay, to convert classical state to quantum state. After converting into quantum state, you'll be having qubits. So you'll be having qubit representation of your classical bits, right? Qubit representation. And after that qubit representation, you'll perform the same thing, same circuit, same stuff you'll perform. So that is your quantum machine learning. And this VQE is also a type of VQC, but with a different mathematical concept. So that's it. So yeah, this, I think the time's also done. So yeah. So this is like the basic overview of all the quantum machine learning and every stuff. So if you're having any doubts, you can already ask me this. Okay.